Hello, and welcome to this course on quantum information for engineers. My name is John Jian. I hold degrees in both physics and engineering, and I have worked as a telecommunications and software engineer for 30 years. Because of this background, I approach quantum technology from an engineer's perspective, a perspective that often makes it the easiest to understand. From this viewpoint, an ideal quantum bit, or qubit, is seen as an information carrier free from noise and errors, which is the source of quantum power. First, what is information? In our brains, information is invisible and feels abstract. Outside our minds, however, information takes the form of symbols, useful symbols. In computers, and in all machines, information is represented by numbers. These numbers are called codes in information theory, though their names change depending on the level of the technology stack we are looking at. If you are an application software engineer, you work with text, images, or general data. If you program in hardware-oriented languages, like C, you work with bits, bytes, integers, and floating-point numbers. I call these hardware codes. For communication engineers, symbols are also hardware codes. As a software engineer, you do not need to know how a binary bit is represented by the voltage of a pair of transistors. But as a communication engineer, you need to understand how the parameters of a carrier wave, such as amplitude and phase, represent a symbol. Mapping symbols to carrier wave parameters is called modulation. Both cell phones and Wi-Fi use quadrature amplitude modulation, or QAM, for short. In both communication theory and quantum information, studies focus on hardware codes, carrier waves, and the relationships between them. In this course, terms shown in green come from communication textbooks, while terms in red come from quantum information textbooks. Quantum information is best understood at the hardware code level. That is the core perspective of this course. But before we get there, we will first build some fundamental concepts and explore the connection between carrier waves and hardware codes. The course begins with the fundamental concepts, followed by a high-level overview of quantum technology in Chapter 2. Starting in Chapter 3, we will explore the carrier level of qubits and examine the qubit readout bottleneck. This bottleneck is the fundamental factor that limits the power of quantum computing while enabling quantum encryption. It is a challenging topic, even for students with a strong background in physics. In the later chapters, we will study several well-known quantum algorithms, including the famous Shor's algorithm. We will also classify these algorithms into design patterns, which serve as bridges between real-world application problems and their solutions at the code level. The first fundamental concept we have learned is that information is useful numbers. We also know the following. First, information is represented or carried by physical parameters. Second, information processing, including computing, is done by changing those parameters. Now we add the third idea: errors are the ultimate enemies of information processing. On a computer chip, the voltage of a pair of transistors serves as the information-carrying parameter. In communication systems and in quantum systems, wave parameters carry information. For example, AM radios use amplitude to represent voice signals. The weakness of these early systems is obvious: we hear noise. That is the limitation of analog technology. Errors are indeed the ultimate enemies of all computers. There are two main kinds. Systematic errors come from how we build devices, and they are usually correctable. Random errors come from unknown sources, what we traditionally call noise, based on our experience with radios. In digital computers, if the measured transistor voltage is something other than 0 or 5 volts, we treat it as an error and assume the true value is either 0 or 5. This approach, ignoring small deviations and correcting the errors, is the advantage of digital technology. We can also build analog computer chips out of transistors. At the code level, analog technology works with real numbers, while digital technology works with integers. An analog computer can perform several real number operations at once and is therefore fast. A digital computer, by contrast, has to round real numbers and is limited by the number of bits used to represent them. but analog computers suffer from high error rates. As a result, they have largely disappeared from everyday use and survive only in a few specialized applications where raw speed still matters. This naturally raises a question: can we combine the strengths of both analog and digital computers while avoiding their weaknesses? The answer is yes. That line of thinking leads directly to quantum computers. Now, let's pause for 2 exercise questions.